Good pre-noon, everyone, and welcome to another one of our Cosmic Conversations. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and I'm joining you from my house to yours for a special presentation featuring the amazing work and one of my favorite objects in the solar system. We're going to be hearing from Michael Nayak. So, Mikey, thank you for joining us here today. We understand you had some video issues earlier, so you're appearing as a avatar icon.
I am indeed, but I'm happy to be here, and I'm very glad to be talking with people about Europa.
Fantastic. I can assure all of you listeners or watchers at home that Mikey is in fact a real person and not a AI or something we've brought in to talk about this stuff. But we might talk about future AI assisting researchers. We wanted to start off our story of Europa a little closer to home, though, checking out planet Earth and some of the really cool stuff we see here. Mikey, one of my favorite facts about Europa is we talk about it having a lot of water. Can you tell us how that stacks up compared to our own planet?
Yeah, so while we have a lot of liquid water right on the surface, Europa is interesting because at first glance, it appears to be just an ice shell. But this is one of the things that makes Europa so interesting from a search for life point of view, is that as we zoom out past the asteroid belt, the solid moons become more interesting than the gas planets. And Europa is particularly interesting because it may have an internal ocean of liquid water. And of course, that's where life on Earth first began, in the water. So we're really interested in what the surface expressions of that water might look like on this icy moon.
Now, I have gotten some people pointing out to me that every week we do a virtual tour of outer space, and every week I announce that I have a different favorite moon, which is perhaps a little bit difficult for me in terms of my commitment to having one specific favorite. But Europa is usually the favorite. And
Excellent.
Can you tell us a little bit about why this is such an amazing moon?
Yeah, absolutely. I've been both personally and professionally interested in Europa for years now. So, the theory is that either through tidal interactions with Jupiter, which is massive and nearby, or through forcing orbital resonances. So there's a resonance between Io, Europa, and Ganymede, these three moons of Jupiter, that some combination of that is generating enough heat under the surface that we're looking at right now to maintain a liquid ocean. And so that's really interesting from a bio and life point of view. If that water is warm, and warm is a relative term, sure. But if there's an exchange between the surface and the ocean underneath, then it's quite possible that there are the ingredients for life there. So that's why Europa is one of my favorite moons. And Josh, as long as Europa is one of your favorite moons this week, I think we're in good shape.
Oh, it is. So we wanted to give you a little bit of a view of Europa. We just flew by and saw that interesting kind of eggshell color surface. Let's see if we can compare it to another one of those Galilean moons you mentioned.
That's a great idea. Yeah, let's head over to Callisto. So we just saw Europa, and we'll be back. But what you saw was kind of a young white-looking surface with some very noticeable features on it. So as we go across to another nearby moon, Callisto, I think we can point out what is so interesting about Europa. So this is Callisto, and as we take a look at this, you'll notice that there's a couple of things that are different between this moon and Europa. And as we come out of the shadow, you can see that, first of all, just the color of the surface is so much more different, right? There's not as much white on the surface. And what that means is that Callisto has a lot more rock on its surface. But there's more, too. This surface we're looking at right now is super cratered. Craters everywhere. And what that means is that it's pretty old, geologically speaking. Things have been hitting the surface for a long, long time, and nothing is removing those craters. There's no resurfacing of the crust. So Callisto, right here, looks just like it did millions of years ago, just more dimpled as the days and years and centuries go on. So freezing that in your mind, now if we can go back to Europa, I think we can appreciate how the surface is different. And you'll see that it's pretty fresh. And so what we're looking at there is this whitish color. And so spectrally, Europa looks a lot like water ice, which is interesting. It's also now, what are these colors? So we've got white for water ice. And as we sort of fly around, you can see that there are these brownish tints on the surface, right? So first of all, comparing it to Callisto, Europa is much, much smoother. There's almost no craters here, actually. And that's what I mean when I say geologically young, right? So these are indicators of change, that it's the same impactor population at Jupiter's orbit, right? And what I mean by that is that Jupiter family comets and long period comets are hitting both Europa and Callisto at roughly the same, size frequency distribution. So you'd expect to see similar cratering. But as we're seeing here, Europa's surface has almost no craters. It's all these long linear features, and these are tectonic features. So the surface of this moon is being constantly refreshed. And there's the factor that's majorly responsible for that is tectonic disruption of the surface, which is a lot like the Earth, actually. And this is one of the things that hints to us that there's more to the surface than might be immediately obvious.
Now, when you say tectonics, I'm immediately called to mind of stuff like earthquakes or cracks on Earth. Is that the exact same process we're seeing here?
Absolutely.
They can't have earthquakes, but
well, we don't know that for a fact, but yes, that's quite possible. So actually, now's a good time as any, since you asked that question. Let's talk about some kind of the classic tectonic features, and those are double ridges. So as you see here, you can see those long lines, right? So if we just pick any one of them and zoom in, let's take a look at what those features look like a little more close up.
Now, folks might be noticing that we're about to do something that is completely cheating in our software. We are turning off nighttime on the surface of Europa. Europa does not glow like this. We're using the open space software, which allows you to do cool things like see the entire surface of a planet. Ooh, so we had Stephen asking, are these dark lines crevasses, or canyons?
That's a good question. So they're a little bit of both. And let's talk about the features. So that long line running across this center there, right? And you can kind of see there's another one crossing it. And that one's even better one to look at. They sort of look like railway tracks, right? Now so that's more of a crevasse, right? But now you see the one that's crossing it like an X. Now that one's much deeper. So that actually tells us something. Okay, but they're both the same feature. And what these are called are double ridges. And we've got lots of examples here, so feel free to fly around between them as I talk here. But you can see as we zoom in a little bit that what we're seeing is sort of a central crack or a trowel that's flanked by two raised edifices. So the ridges are about 200 meters to 4 kilometers wide, depending. Yeah. And they're about 100 meters high, but that's not what's impressive. What's interesting is they commonly have lengths of over 1,000 kilometers, which is pretty remarkable if you consider that Europa only has a diameter of 3,000 kilometers. So what we can take away from that is that whatever's causing these ridges is a pretty global phenomenon. So, and this sort of touches on Stephen's question, what forms these double ridges? There's two models that geologists are looking at, and the first is based on tidal stress. So Europa's orbit around Jupiter is not exactly circular, just like the moon's around Earth. And just like the effect that the moon has on the ocean, right? It raises and drops tides. Jupiter has the same effect on Europa. And now because both the distance and direction of Jupiter oscillates relative to circular motion of Europa, it's going to set up a periodic stress, or what we call a diurnal tide, which we see right here on Earth because diurnal for daily, right? So these tides are going to change across the course of a day. We're going to have a high tide. We're going to have a low tide. So there's a rotational torque that's created by Jupiter on Europa, and that's going to have tectonic effects like these features that we're seeing. You can see them crossing each other, right? Which means that you can tell right there the direction changes frequently. So imagine if you had, Josh, imagine you had a stress ball in your hand, right? And you squeeze it. Well, now if you imagine that stress ball is made of ice and you squeeze it hard enough, that surface is going to crack, right? The ice is going to crack. Well, if there's an ocean underneath, water is going to seep up from the underlying ocean, fill the crack, but then it's going to hit hard vacuum. So that's going to freeze into this slushy, slurry kind of thing, right? But remember that now we're talking about diurnal tides. The tidal forces are periodic. So every day on Europa, Jupiter pulls and squeezes, just like your hand on that stress ball. So there's a crack that's already there in the ice. That crack is going to get compressed and pulled apart, When it's compressed, it's going to smash up all that slurry ice inside and squeeze it up and outward, sort of like toothpaste from a tube. And that's going to freeze and crack, grow a little taller, freeze and crack, grow a little taller, until it makes that double ridge on top of the initial crack.
Wow. That's amazing.
Isn't that interesting? Yeah. It's so cool. And so that's one of the things that makes Europa so interesting, right? Is that there's a lot of dynamic interaction between the surface and what we think is underneath. But that ice melt, is what's going to create that central trough of the double ridge that's so characteristic, and it's all over Europa. They stretch all over the surfaces, and that's what I mean by tectonic terrain. The common denominator of Europa tectonics are these double ridges that are associated with tides and tensile cracks in the crust. And Josh, I believe you mentioned California earlier, and I said yes, It's exactly like that. So just like ice is raised up in these double ridges, ice is also going to be subducted down, and it's going to disappear under what we call strike-slip faults. The San Andreas Fault here in California, you guys are up in the Bay Area, I'm down in Los Angeles. The San Andreas Fault connects us both. That's a great example of a right lateral strike-slip fault. And this sort of fault swallows land up periodically, and that's sort of what's rewriting the surface of Europa. It causes big sections of Europa to essentially disappear over time and be rewritten with new ice that's completely blank. And so going back to our initial look at Callisto, we think this is one of the mechanisms by which Europa essentially erases craters from its surface.
I had as a person who loves imagining standing on other worlds, if you were to stand at the bottom of one of these gigantic double ridges and look off in the direction, they're so long you wouldn't see the other canyon wall, right? You'd basically see like standing at the bottom of the Death Star trench.
Exactly, right. And they're only about 100 meters high, right? Because that's going to be determined by the tensile stress of the ice.
Sure.
So they're not super high, but 100 meters is maybe
still
10 stories tall. Yeah. So you're standing in the middle of a Death Star trench that's 10 stories high. And that's just going to go on. It's going to wrap around the surface.
That is really cool to think about. Okay, we saw another one of the images you mentioned right along the side here, which might be a good transition. Some of these seem to have a weird scalloped edge to them. Can you tell us about those?
Yes. So these are a fascinating feature called cycloidal lineaments, or cycloids. So if we zoom in on that, it's kind of like you asked a kid to draw a cloud, right?
Or me.
Fair. Me too. I'm not much of an artist. But yeah, they're curvy and scalloped. They go up and then down. They reach a peak and then go up again and then come down again. Okay, so yeah, cycloids. Now, I love these features because back in the 90s, these are actually earlier than that. These are one of the first features that started folks thinking that maybe there's an ocean underneath. And here's why. So the scalloped edges there that we see, those curly, this is a great view of them going all across your screen. You can get an idea of how long they are. And these scalloped edges actually follow the diurnal variation of tidal stress that we were just talking about.
Wow.
So how are these features created? Well, the first step is just like we talked about. Tidal tension of Jupiter flexes on Europa. It exceeds the local strength of the ice, and things start with a crack in the ice. And just like we learned in high school physics, shear is a perpendicular force. So the crack is going to propagate perpendicular to the local tidal tension. But we got to remember, Europa's moving, Jupiter's moving, so the vector of that tidal tension is going to shift. And that's what creates this shape. As the Europa day wears on, the shear stress will still be perpendicular, but the direction of that stress is now changing. So the ice is actually not going to propagate in a straight line, but it's going to propagate in an arc at the speed of about, a few kilometers a second, something like a few kilometers per hour, something like a fast running pace. Now, at some point in the day, right, just like here on Earth, we got a high tide, we got a low tide. So sure. Europa is going to, the stress is going to fall below whatever is necessary to keep the ice cracking. So now we have no more crack propagation. A few hours later, it'll pick up again, but in a different direction. And that means the crack propagation is going to resume at an angle to the direction at which it initially stopped. And that is the edge. That's the scalloped edge.
Point.
Exactly. That's a sharp point. So that point is still weak. There's still a crack there. So it kind of makes sense that that's the weakest point in the ice. That's where the crack will start again, but now it's going to be in a different direction.
Wow.
So the end result of these series of arcs, each arc, interestingly enough, corresponds to 1 day on Europa, which is about 3.5 days here on Earth. 1 day's worth of propagation.
Wow.
And then those cusps between them are basically where the tidal stress drops below a critical value, and it can no longer puncture the ice. So we see these chains of arcs all over Europa. They're typically about 100 kilometers long. They're connected at the cusps, and they extend, thousands of kilometers.
I see some of them perpendicular to each other. Does that
Ah,
follow predictions, or is that something that's really strange? Because it seems really
it does.
strange.
Yes, absolutely. So actually, can we go to the equator?
Can indeed.
I believe we had some cycloids there. So yeah, you folks have got the idea now of these long lineaments, right? And those are typically at fairly high latitudes. But if we go down to the equator, we're going to see a different type of cycloid. They're going to be more mashed together. We call them boxy cycloids.
I might need some help with my European geography.
Oh, sure.
Where-
Actually, you can see it right there if you just
great.
zoom in.
Okay.
They're going to look a little bit different. We're not quite there. But as we go around, if we see them, I'll point them out.
Okay.
But like I said, this was the first strong evidence for that liquid ocean, because the ocean is required to get adequate amplitude on those tidal features, on those cycloids to form. So if there weren't an ocean, those cusps would look sort of like you asked a kid to draw mountains. They're going to look like triangles, up, down, up, down, up, down, much sharper, pointier, less arcuate. So the fact that those features are long and are in arcs like that is really an exciting pointer that there's a liquid ocean underneath, driving the amplitude of the ice.
I'm going to bring back Europa night, because that'll at least help me figure out where my poles are.
There we go, right there.
This looks equatorial.
That is it. Yep, let's zoom in on that. So these are boxy cycloids. You can see they're still archy, they're still curvy, but they're squashed together. And we actually expect this. We expect, with tidal modeling, we expect that cycloids that cross the equator are more scrunched up and not symmetrical, right? We find this boxy morphology is expected. And that kind of makes sense because the equator is the widest part of Europa, the bulkiest part. So we expect to see a different geometry than we do farther up. So this is actually pretty valid proof that the tidal mechanism that I just talked about is what's actually happening on the surface. Okay, so that's cycloids actually. So those are both tectonic features, right? So there's two major parts of European geology. So how about we skip over to some chaos terrain and take a look at that? Sounds cool, right? Chaos.
Great example of the chaos right over here, which is
perfect. Yeah, so that is that's beautiful. So this is, you can see it's framed by the tectonic features we talked about. You can really see those double ridges out there. But what is that jumbled up stuff in the middle? And we call that chaos terrain because that's essentially what it looks like. It just looks like a bunch of stuff. But as we zoom in, though, and I believe you might have a picture of this, an overlay.
Yes, indeed.
So you can see that there we go. That's beautiful. That shows you what's sitting right there on the surface. The pre-existing planes of ice have been disrupted into these polygonal ice blocks, and you see them everywhere, right? These blocks or rafts of ice are set within a matrix of mound-shaped material. So you'll hear the phrases rafts and matrix a lot when we talk about chaos terrain. But just think about a whole bunch of icebergs floating in like a slushy. These blocks of terrain have been tilted and rotated and translated. We don't fully understand the formation of chaos terrain either, but from an exploration standpoint, this is where the money is. If there's in fact an ocean under the ice, it probably comes closest to the surface right here because there's a ton of fissures in the ice that we're looking at right now. So a drill would have to work less to punch deeper. And we're very interested in understanding the relationship between these blocks, these floating icebergs, and the ocean underneath. So cool. Let's take a look back at the surface now, and you can see that chaos terrain. And all of this is fueling kind of a debate between scientists. Is the ice shell on Europa thick or is it thin?
Before we get too far away, question. When we look at the surface of Europa, we see this kind of eggshell white dun color. But in the image you just showed us, it was very dramatically different. Can you explain some of what that means?
Yeah, so some of that is false color. Right. And so the reason is we're trying to highlight where these different colors help us to highlight what areas are morphologically different from the others. So good question, because now if we go back to the surface and just look at like what Europa really looks like, you see that brownish stuff. When we look at that brownish stuff through a spectrometer, we see it's rich in salts such as magnesium sulfate, magnesium carbonate. And that's exciting because that's what you would expect to see if there were tiny cracks in this ice shell and water from the global ocean is seeping out and evaporating. You would expect to see
that seems pretty exciting, though, if there's liquid water coming up.
Yeah, that is exciting. So, right, so that's one of the things that Europa Clipper, which is going to be the next mission to Europa, can hopefully get us a better understanding of.
Okay.
So we've got...
We had a couple other features you wanted to check out. A dilational band or a double ridge? Which sounds cooler to you?
Let's take a look at a dilational ridge, a dilational band, because those are fairly interesting. And because what we're seeing there are spreading. They're essentially tectonic features.
Oh, these are some cool looking ones.
Yeah. So there's two things that are sort of driving the way the surface looks on Europa. The first are tides, and tides pull and push, pull and push. So here you can see a really good example of double ridges, but there's many of them all in a row, all next to each other. And there's a whole bunch of different reasons that we think might be responsible for these. You know, is there warm ice that's rising through the shell kind of buoyantly? Are these particular places where the ice is structurally different, and that's what allows it to spread like that? There's a lot of debate and modeling and math, but truthfully, the only way we'll know what's down there is to set a lander on the surface, drill down, probably into one of those chaos regions, send a probe down into the water, and see how deep she goes.
Can you tell us a little bit about what brought you to Europa studying? What made it jump out of all the other moons in our solar system?
Absolutely. So I've been interested in Europa since I was a kid, and I've always felt that, you know, if you want to look for life, look where there's water. And this is one of those fascinating places where that's actually true. So I started looking at Europa when I was a planetary scientist, and now actually it's a good segue into what I'm doing now. Is I'm the principal investigator of this project called Energy, which is the Europa neural net expansion for robust geologic identification. Big acronym. Basically, it's a small, agile team with a little bit of NASA funding, and we're trying to do a couple of things. So what's super interesting about Europa is these images we're looking at, Josh, these are 40 years old. These are from Galileo. We don't know what's happened on the surface of Europa since. Not a lot will be different, but anywhere that is different. Yeah, right, maybe. So Europa Clipper, which is a NASA satellite that's going to be orbiting Europa. It's going to launch in about 5 years, get to Jupiter in about 10. But anywhere that is different, when Clipper looks at it, is somewhere that is changing very actively, because 40 years is the blink of an eye in geologic time. So Energy is trying to use machine learning algorithms specifically tuned to Europa to rapidly and immediately highlight these areas of feature change, right? This crack is new, this feature has been swallowed up. Things like that can be very exciting because if we can identify it early in the mission, we can schedule low altitude, high resolution flybys of those locations and really get an idea of how dynamically the surface is changing. So the science team for Clipper right now has a plan of what they want to look at, and we want to use machine learning and artificial intelligence to help inform that plan with data from the very first new orbit, because Clipper is going to be flying around for 3 years. So we want to use machine learning to say, hey, this is different. And if it's different and continuously different, well, that's probably a place you want to drill in the future, right? Because that's a place where the ocean and the surface are probably actively exchanging materials and interacting together.
Speaking of the changing surface, how do we estimate the thickness of the ice, and what is that estimate?
Yeah, so we think that the ice actually conceals a global water ocean, and that outer water shell is somewhere between 80 and 170 kilometers thick. And where that started was with Galileo. Galileo took a bunch of gravity measurements of Europa, which gave us the knowledge that Europa is internally differentiated, which means there's layers to it. Kind of like the Earth. The Earth has 3 layers: the crust, which we're all standing on, then the molten core at the center, and the mantle in between. Gravity measurements of Europa told us that the surface of Europa is differentiated. It's not just a solid block of ice. And then we looked at features like cycloids, like we talked about, like chaos terrain. And then tidal modelers essentially said, okay, well, what does the thickness of that shell need to be in order to create this surface expression? And then through inverse modeling, we've arrived at an outer water shell somewhere between 80 and 170 kilometers thick. So We have a solid ice shell, a possible global liquid salty water ocean underneath, and each of those words has a specific and very exciting connotation for the possibility of life underneath this strange looking moon. But hopefully over the last couple of minutes, we've been able to get an idea of sort of the two general categories of European surface features. We've got the tidal features, tectonic features. Those are usually global. And then we've got patches of this chaos terrain, icebergs floating in a slushy. And those are geologically possibly changing. And so those would be really interesting to go back and look at. And so that's essentially what I'm working on right now. Is training a machine learning algorithm to essentially be a second-year grad student in geology and look at images of Europa, just like you and I did, and automatically detect features like the ones you and I talked about. Craters. This is a crater. This is a double ridge. This is a tectonic feature. This is chaos terrain. This is a matrix. This is rafts. And once the algorithm can recognize them, distinguish them, it can then hopefully tell us what's changed over time. And if I may, one of the things that makes that hard from a machine learning point of view is that, as it turns out, we only have about 186 images of from Galileo of Europa. That's what this whole map is built off of. 186 images. So if anybody speaks machine learning, they know that's an incredibly small training data set. Some would say impossible, because machine learning algorithms are known for their work with big data sets, and I'm talking millions of images. So actually, I think I'd like to show you an example of what energy has been able to do. If you have that image, I think it'd be kind of interesting to look at.
I can try and dig it up if you give me a couple seconds.
Oh no, that's okay. It's in the Facebook picture, but it's essentially able to label simple and complex craters, and that's machine done. And we're currently working on machine recognition of the features we talked about today. So cycloids and double ridges and chaos terrain.
Okay, so I'm downloading it as we speak. We can show it to everybody momentarily. But one of the questions that came up was the subsurface ocean. Would you describe it as more slushy or liquidy?
That's a good question. The short answer is we don't really know. Right now we have physics-based models, and depending on which and there's uncertainty in all of the parameters, right? So if you adjust the uncertainty on one parameter, you might end up with the slushy. It's mostly a question of depth, right? We expect that closer to hard vacuum, especially if there's an actual cracks that expose the liquid underneath to the vacuum above, that we're going to see more of that slushy stuff. But as we go deeper, then we're going to see a global ocean, right? Because there's heat being pumped into the ocean by tidal interactions with Jupiter. It's just like when you flex on that stress ball over and over and over, it's going to get a little warm in your hands. So we don't doubt that there's liquid water down there. We don't think it's slush all the way down to the mantle. It's just a matter of, well, how deep are we going to have to drill to get to water? And that's probably one of the biggest debates about Europa at the moment.
Now, I know for myself, in talking to you and preparing for this, I feel like I built my lexicon of understanding some of these surface features up a little bit. And
that's great.
Our folks at home, I would say, if you really thought this was a cool program and you want to do some more experiencing for yourself, download OpenSpace and give it a shot. We are using information that is part of OpenSpace. You too can fly around Europa and try and figure out a little bit more about what this surface is like. And know that when new information becomes available, maybe from Europa Clipper, it's going to get integrated into this software. So if you are a budding aspirational surface explorer, now is an awesome time to be playing with this kind of software.
Absolutely.
If you folks are interested, we would love to hear from you. We've got a survey coming out. I think there's a link already in the comments. Today is your last day to get a NASA sticker. So if you're one of the first 30 people to respond, they will mail one to you. NASA meatball stickers are super cool. They never go out of fashion. We had a question pop up. Hopefully more probes can be sent to Europa and the other moons, but Europa lander is a possibility. Would a miniature drone helicopter be able to operate on the surface? Is there any gravity on the surface of Europa?
Yeah, there absolutely is gravity on the surface of Europa. I think what would be more interesting, and this is just my opinion, is that rather than a helicopter that goes over the ice, I think a submarine that goes into the ice and into the water would really teach us a lot. But there certainly is gravity on Europa. And the thing that makes a Europa lander challenging, and this is the reason why we're going to send Clipper as an orbiter first, is just the radiation environment is so tough because Jupiter's right there. That first of all, it's really tough to get into orbit around Europa. In fact, Clipper is not really going to orbit Europa. It's going to orbit Jupiter and just sort of sling really close. So orbital mechanics wise, it's tough. But also, you know, if there's a drill, if there's a submarine under the ice, you want a satellite in orbit to sort of make contact with it, ping it every so often. Hey, are you alive? Hey, yes, I am. I'm still here, still doing stuff. Here's my data. And that's just so challenging because of the radiation environment, and orbitally, orbiting Europa is tough. So I think NASA made a decision a few years ago that, okay, before we go full up lander, we need to go orbiter and really learn how the surface is changing and where are good access points to drill. And then hopefully, you know, Clipper will start giving us those answers in 8 to 10 years. And then I would love to see a Europa lander in my lifetime.
Well, one last parting shots for our Europa files out there. If you want to see Europa, you really don't need a spacecraft to do it. If you have binoculars or a telescope, Jupiter is up when the sun sets right now. If you go out, point your telescope or binoculars at Jupiter, you might notice 4 points traveling around it. The second farthest from the surface of Jupiter would be Europa, and it is a really fun thing to pick out for yourself.
Nice. Yep, that's absolutely right. Galileo did it in the 1600s
with a worse telescope than most of us have hiding somewhere in our garage or our friend's garage.
Indeed. Amazon can beat what Galileo had back in the day very easily.
Well, Mikey, thank you so much for introducing us to the surface of what might be, for the next few weeks at least, my absolute favorite moon in the solar system. Any parting shots for our audience? Anything you want to say?
No, I think Europa is one of the most interesting places in the solar system, and I think just keep your eye out. I think Clipper, as we start to get closer to Europa Clipper's launch, which is still about 5 years out, I think you're going to see a lot more folks studying and interested in this. So stay tuned. We're learning more every day.
That's fantastic. Thank you so much for joining us here. For those of you at home, thank you for tuning in. Stay home, stay happy, stay healthy. The museum, we are very excited, is going to be reopening to the public on the 23rd, and maybe some of you will be able to swing by. Thank you all for joining us, and have a wonderful rest of your day.